wake of rapid advances in glass fiber waveguide technology, commercially available glass fibers have reached a level of performance quality sufficient to exploit the many potential advantages offered by fiber optics as a medium of military information transfer. This is the subject of the Navy's Airborne Light Optical Fiber Technology Program, Project Aloft. The program, sponsored by the Naval Air Systems Command, was inspired by earlier investigations of fiber optics technology as a practical solution to the common problems associated with internal signal transmission in high-performance aircraft. Major program objectives would seek to prove operational immunity of fiber optics transmission lines to radio frequency and other forms of electromagnetic interference. Aloft would verify that multiplexing for signal transfer is indeed feasible due to the wider bandwidth. Thus, a significant reduction in number, weight, and complexity of transfer paths and cable connectors as compared to existing wire systems. And finally, the program would evidence increased system performance and reliability, particularly in the operational carrier environment, as well as providing a valid measure to gauge the feasibility of full system applications. These were the objectives, and this is how it was accomplished. Time, March 1974, at the Naval Electronics Laboratory Center, NELC, San Diego. Here, as the activity designated to lead the two-year effort, NELC managers and engineers were engaged in consolidating plans and objectives into a formal development program. By June, a plan of action had been clearly defined, based on the best available government and industrial resources and reinforced by prior environmental testing of candidate components. Aloft would focus on the navigation and weapons delivery system of an A-7 military aircraft, where 115 signals, normally transmitted over individual wire channels, would be multiplexed into 13 fiber optics channels, converging at one interface connector. Time, August 1974, and a contract award to the IBM Corporation, Owego, New York. The specific task: design, develop, and fabricate an electronically multiplexed information transfer subsystem to provide communication over fiber optic data links between the aircraft's NWDS tactical computer and peripheral avionics equipment. At the same time, Vought Systems Division Dallas was contracted to formulate a comprehensive installation plan to integrate Aloft into an operational A-7 for the flight test phase. Also at this point, the Naval Weapons Center, NWC China Lake, as the responsible agency for configuration management of the Navy's A-7 operational software, was tasked to monitor the IBM development effort and adapt the software to the contractor's design. Time, year's end, 1974. At IBM, final system design was complete, candidate system components determined, and individual component subcontractors selected. At the Valtech Corporation, West Boylston, Massachusetts, manufacturing of the Aloft fiber optic cables was underway. Cable specifications, determined by computerized parametric evaluation, called for bundles consisting of close tolerance individual fibers covered by a protective jacket. Prior analysis had verified that this cable configuration would satisfy acceptable loss tolerances between the light source and the detector, allowing that some of the 13 cables would pass through as many as 5 coupling points, each imposing some degree of loss. Because of this, performance and reliability of the various coupling devices were highly critical factors in the component design process. First, IBM designed and fabricated connector units to link the fiber optics cable to the light-emitting diode and photodetector components supplied from available industrial inventories. Next, specialized connectors were necessary to route fiber optics cables through the pressurized cockpit bulkhead. NELC recognized this need early in the program and answered the requirement by a design superior to any fiber optic bundle connector available for this application. The same connector can be used to pass cable through hazardous cargo compartments, a valid design consideration with fiber optics because in the event of battle damage, there's no sparking, heat, or fire to initiate secondary damage, as would occur with wire systems. The unit features an average 3 dB loss while maintaining a pressure integrity up to 1,000 psi and was fabricated to the NELC design by the Selectro Corporation, Mamaroneck, New York, at minimum cost to the Navy. In answer to the third connector requirement, a subcontract with ITT Cannon Santa Ana produced a rack and panel multi-channel connector to interface with the system's computer. This hybrid configuration not only provides for Aloft's optical interface requirements, but includes provisions for 30 standard electrical contacts within the same unit. Meanwhile at IBM, design and fabrication of discrete transmitter and receiver circuits was in progress to provide the optical links between the computer and peripherals. The light-emitting diodes and photodetectors, mounted on their respective circuit boards, are mated to the fiber optics cables by the special connectors. So these were the essential components. Fiber optics cables, 3 types of connectors, light-emitting diodes and photodetectors, along with the appropriate circuitry needed to convert electricity to light and conversely, light to electricity. But let's look closer at how they perform in actual system operation. Signal information originating at the peripheral avionics equipments is passed to the externally mounted adapter units, where many parallel channels are electrically multiplexed to a serial channel. The serial signal modulates current through the light-emitting diode, producing a proportional light signal. The generated light then enters the fiber optics bundle, consisting of many individual fibers. Each single fiber is enclosed by an outer cladding glass of a lower refractive index, which acts to contain and reflect the propagating light energy. In actuality, the propagated energy is the sum of a multitude of single light rays that literally bounce within the fiber along varied paths. At the various connector junctions, the ends of the fiber optic cables are physically separated by a small air gap, which in effect eliminates the contact discontinuity problems common to wire connectors. For the Aloft configuration, the 13 fiber optic cables pass through the single multi-channel connector at the computer interface, where one is linked to the appropriate circuitry for analog signal transmission, and the remaining 12, 6 to transmit and 6 to receive, to the digital circuitry containing the LEDs and photodiodes necessary for signal conversion. Time, October 1975, and a gathering of government and industrial representatives at the IBM facility to review the results of preliminary software and hardware acceptance tests. This essentially concluded the hardware development phase of the Aloft program and set the stage for final acceptance testing at LTV Dallas. LTV, in addition to preparing the aircraft installation plan, was tasked to conduct the ground simulation phase of the program. Here, testing of system software and hardware in compliance with operational flight and test programs supplied by NWC provided the foundation to measure system performance against government acceptance standards, as well as develop criteria for later flight test safety considerations. various system components and peripheral equipments were subjected to testing in conjunction with the facility's A-7 simulator, which closely resembles the actual aircraft configuration. During the same period, the existing wired system and the Aloft fiber optics version were subjected to selected temperature, vibration, and EMI environment tests to simulate the punishing in-flight conditions. In both the environmental and final acceptance tests, the Aloft system performance was equal to the fleet configuration under identical circumstances. Time, February 1976, at the Naval Weapons Center, NWC, China Lake. Arrival of the Aloft hardware at NWC launched the third and final program phase, a 6-month period devoted to intense ground and flight testing. The system was first introduced to a series of validation tests as the primary method to determine aircraft system integrity prior to flight testing. Employing NWC's aircraft simulator over a dynamic range of realistic in-flight parameters, 2 versions of the Aloft computer were evaluated under identical conditions. 1, a modified version of the existing fleet configuration capable of being used with copper wire and non-multiplexed data transmission. And second, the same computer further modified to be usable with optical fibers and multiplexed data transmission. Additional tests of the copper-wired version were conducted in the assigned A-7 test platform to supplement simulator testing data. With completion of ground testing, 2 series of in-flight tests were performed using the fleet configuration and the copper-wired Aloft version. The data gathered from a total of 20 flights provided previously unavailable baseline reference data for comparison against the fiber optic system during the final flight test phase. Time, March 1976, and the conclusion of baseline flight tests. This signaled the go-ahead for aircraft installation of the Aloft fiber optics configuration. Bulkhead modification, mounting of the 5 adapter units, and adaptation of fiber optics conversion components all joined to prepare the system for the impending flight tests. The first sequence of tests were conducted to verify the system's operational integrity in the airborne environment and to gather navigation and weapons delivery performance data under conditions identical to the initial baseline tests. Time, 6 May, and briefings for invited representatives in preparation for range demonstrations where the system would be employed in realistic tactical exercises to provide the first comprehensive view of Aloft in action. The demonstration consisted of 5 tactical exercises against a stationary target on the desert test range. Target closures occurred at different approach angles and velocities, including bomb drops at 45, 30, and 15 degrees. Finally, at a 20-degree approach angle, 2.75 rockets were launched with equally successful results. In each instance, the Aloft system configuration was equal to prior tests employing the existing fleet configuration, and in the pilot's words, I could see no difference. Time, end of demonstration, and the beginning of a new dimension for internal communications in operational Navy aircraft. Project Aloft, proof that the inherent benefits of fiber optics technology offer the promise of improved reliability, maintainability, survivability, and immunity to radio frequency and other forms of electromagnetic interference. Words that spell increased effectiveness for our airborne military forces.